So question 9.20, basically which of the following molecules will have ideal and non-ideal bond angles, and the ones they give you to look at, boron, trichloride, what else do we have? Got carbon tetrabromide, iodomethane, tellurium, and sulfur. So what we need to do, what we need to look at to decide are these molecules going to have ideal or non-ideal bond angles, is we have to draw the Lewis diagram and figure out, do they have lone pair electrons? And so if we look at the Lewis diagram for boron, trichloride, we've got 1, 2, 3. Put the lone pair electrons in for the chlorine, and we'll see that we've got 3 electron domains, 3 molecular domains, and as a result, our bond angles, right, should be about 120 degrees. It'll be pretty close to ideal in this trigonal planar molecule. And we'll see something similar when we go to the carbon tetrabromide. We would see that carbon tetrabromide has 4 electron domains and also 4 bonding domains. So its electron domain geometry would be tetrahedral and its molecular geometry would be tetrahedral, and we'd expect, you know, approximately, given that it's tetrahedral, we'd expect to see about 109.5 degree bond angles in carbon tetrabromide. There shouldn't be any deviation. If we look at the iodomethane, however, that's going to be a little bit different. So the iodomethane, we would see that, sure, we still have 4 electron domain geometries. And so we're going to be tetrahedral with respect to our electron domains and tetrahedral with respect to our molecular domains. However, due to the size of iodine's much larger. It's got a much larger atomic radius than hydrogen. It'd be taking up more space, pushing down on these hydrogens, pushing the hydrogens closer together. So we'd expect to see these hydrogen-carbon hydrogen bond angles, right? We'd expect to see this bond angle, for example, between these two hydrogens would be less than 109.5, simply because we're trying to accommodate the much larger atomic radius of iodine next to the carbon. And if we look at the last 2 examples, the tellurium compound, let's see, we've got tellurium, and we'll have a trigonal bi-pyramidal electron domain geometry. And our molecular geometry would just be seesaw shaped. We will only look at the bonding electrons. And right, so our trigonal bipyramidal is with respect to our electron domain geometry. We've got 5 different domains of electrons. With respect to our molecular geometry, we're just seesaw. We're looking at the 4 bromines. And again, we would expect to see a deviation from 180 degree bond angles here and the 120 degree bond angles here because, right, these non-bonding lone pair electrons take up more space than bonded electrons, so they would be pushing to try to accommodate the space of these non-bonding electrons. They'd be pushing on this bromine, tellurium, bromine bond, so we'd expect to see that to be greater than 180. And the same thing, they'd be pushing here on these bromine bonds here. And so we'd expect to see first greater than 180 here, and then here we'd expect to see less than 120 degree bond angles there as a result of accommodating that lone pair of electrons. And for the last compound, we'll see that, and this is going to be very similar to water, we have 2 non-bonded pairs of electrons. So our electron domain geometry, 1, 2, 3, 4, is tetrahedral, but our molecular geometry would be bent because we only have these 2 hydrogens to account for. But again, right, because these electrons, these non-bonded electrons, take up more space, they're going to be pushing, to try to accommodate these, they're going to be pushing these two hydrogens closer together. So again, we should expect to see less than 109.5 degree bond angles for this compound. So that's what we need to consider. We need to, number one, draw the Lewis structure, and then number two, look at, in this case of the iodomethane, the size of iodine relative to the other compounds, and then the cases of the next two compounds, do we have lone pair of electrons? Lone pair of electrons take up more space than bonded electrons, and as a result, they're going to influence the bond angles of the molecules that remain, or the elements that remain bonded to the central element.